Hi, so I'm Julien. I work for Datadog. And today I'm going to talk about the advent of the open data lake. So a little bit about me and the context. So I've been a long time contributor to ASF project. Believe it or not, I'm an Iceberg PMC member. I started the Parquet project contributing to starting Arrow and more recently OpenLineage. I contributed to a few of those other projects, Calcite and Drill. And I contribute both to the ASF and the LFAI and data, which is a sub-foundation of the Linux Foundation focused on the data project. Oh yeah, and it's going to be a long story because I started using Hadoop in 2007, so we are going to go all the way back there. So first, talking about the advent of the open data lake, I'm going to start with talking about how we built a database from the ground up back in the day on top of Hadoop. And then I'm going to talk about, meanwhile, things have changed. Technologies have changed and all that, and how that influenced things. And then I'm going to talk about how you build a database now with all those open source components that exist. So old school. Right, if you think of database, when you do query evaluation, and here I'm thinking OLAP, right? We're talking about OLAP style database. You parse the query, you get the syntax, there's a semantic layer, you get what are the tables, what are the schemas, you get a lot of information to execute the query. Then it goes through the optimizer, produce the best plan, and execute it against your query engine. So if you look at the steps, start from a query, parse it, turns into a syntax tree. You get metadata about the tables, you send it to the optimizer, generates a plan, we give the plan to the execution, how to do this join by scanning the two tables, joining them together, and evaluating the plan. So that's the general idea, how you build a database, seems simple enough. And back in the day, so remember I said we're going to start with Hadoop. So we are using Hadoop to store data. Hadoop was the way you could store a lot more data, a lot cheaper, and it was great for looking for a needle in a haystack with no plows, right? It's a very blunt tool, very throughput oriented, not latency oriented at all. And it's just a bit slow, but it's very flexible, it's very composable, so composable that you can actually implement SQL with it, right? You can take your parsing and then you turn your plan into a series of MapReduce jobs. And so it's kind of slow and sequential, but it gets the job done. And that's how the Hive, the initial version of Hive, got implemented, right? You parse the query, transform into a chain of MapReduce jobs, store in HDFS, done, right? It works, but it's not very efficient. Right? It's not fast, it's not efficient. And so if you remember, over the next few years after Hive was initially released, a lot of effort was put into making Hive more performant and faster and be able to do lower latency queries. And for that, you need to work on the optimizer, build the best plan, take advantage of pushdown, and try to avoid scanning all that data. You need a good interchange to exchange data, be able to do parallel execution, exchange data between nodes in an efficient way. You need a column storage on HDFS so that we can avoid scanning all the data and have quick access for the OLAP queries. And you need to use vectorization to enable the query engine to execute fast and take advantage of modern processors. So, and all of those components are pretty complex, right? An optimizer works at two levels. One, the rule-based, right? The things you always want to do, like pushing filters before the join, right? You want to avoid doing the join before you drop data. And the cost-based things that depend on context, like ordering what is the best order depends a bit on how big each of the tables are, what are the big tables, the small tables in the join, and then you change the order, it can be more efficient, and change the join implementation. The vectorized ID came out of the MonadDB paper, so this is an illustration from the paper. And the general idea is that processors don't execute instructions sequentially, right? They start staggering the execution, so they start executing the next instruction before the previous instruction is finished. And so it's kind of clever because, you know, the processor is a surface area, so you don't use all the transistors at the same time, so you can stagger execution like this. However, if you have any dependency between two instructions, you have to wait, right? If the next instruction depends on the result of the previous instruction, you have to wait. Which means if you want to take full advantage of pipelining, so this process is called pipelining, you want to make sure you organize your plan in a way that's going to avoid dependencies between instructions. That means anything that is an if in your code, right? An if, anything that is a virtual function call, like typically if you have an evaluation tree with operation, and this is a jump that depends on the type of the data. Or a lot of things like this are going to create slowness, right? Instead of being able to go at full speed, you're going to going 1/10 the speed of the processor. And the second things that modern processors do is using cache. So every time the processor has to fetch data out of the main memory, it also has to wait because the processor processes faster than it can fetch data. So it has cache. So the other thing that you take advantage of with vectorization is to reduce the amount of fetching data. Because if you work on one column of data at a time, or a few columns of data, you can have better locality of the execution and do more CPU operations in between fetching data from the memory. And so you do less waiting and you take more advantage of the processor. So that are the two main things that drive the need for vectorized execution, which is instead of evaluating operation one row at a time, you're trying to look at columnar evaluation and be able to do tight loop when you do the same operation and again and again and again without data dependencies and separate the data dependencies from the execution. The other component I talked about is columnar storage. So when you have a columnar storage, instead of having a row layout like traditional databases that were optimized for read-write, you have a column layout. That means when you do a query that accesses only a subset of the columns, you can do efficient skip and read only those columns and go a lot faster than if you have to read. Let's say you access only B and you do a lot of small jumps. Instead, you just go to the B, read all at once, and it's a lot more efficient. And the last piece is the efficient data exchange. The one thing you want to avoid, since we're building this distributed query engine, we want to avoid like high cost of serializing, deserializing data and sending it over the network. So that's all it took, right? Like if you look at Hive as an example, all those things were worked on for years, right? To make it efficient, and from this initial naive implementation that worked, make it an efficient query engine. Meanwhile, a lot of the ecosystem has changed because one of the key design aspects of Hadoop was to move compute to storage, right? The main idea is like, oh, you need to move compute to storage so you can fast read and write and things. And data is immutable so that it's a lot easier to scale this and you don't have to worry about synchronization as much between machines. It's tying storage and compute because you move compute to storage, right? So the CPUs that are on the machine that stores the data is the one that does the work. And it's because it's MapReduce, it's reliant on discrete steps persisted on disk, right? It reads, writes to disk, then does the next operator, reads from disk, writes to disk, and so on, so which creates a lot of latency in the execution, right? So you don't need transaction when data is immutable. It makes things easier. It's great. Turns out people like transaction, especially when they do SQL. It's very convenient to do a lot of things, and having things not being able to change at all after they are written creates a lot of contention. The other thing is we store coupling storage and compute. And by the way, it's just not just Hadoop, right? Around the same time, we were using Vertica, which is one of the early massively parallel OLAP engines, and or the early version of Redshift had similar idea, right, of moving these compute to storage. And so we're coupling storage and compute, so when you scale, if you need more nodes in your in your cluster, you adding storage and compute in the same amount, right? And so when you get more users on your cluster, they get limited by how many CPUs you have per disk. And so whenever we created the next iteration, right, we buy machines, we deploy them in a data center, whether it's for Vertica or for Hadoop, you're saying, oh, tell me how much CPU you need per disk, right? Like, are you doing CPU intensive workload? Are you doing IO intensive workload, which you're reading a lot of data, but you're not processing a lot of it? And you have this ideal storage ratio, so you get the right machine. And then, of course, as soon as you deploy it, you get stuck with this ratio, right? And so if there are more people who start using the cluster for the same data, there's get a lot of contention. If you need to store more data, you add more nodes, and then you don't use all the CPU. You have a lot of wastage. So there's this all built-in constraint on having coupling storage and compute that creates a lot of contention between users and in cost management of those things. So during that time, technology has evolved, right? One thing that happened is the network got faster than the disk got faster, right? So the ratio changed, right? So now it didn't make as much sense anymore to move compute to storage, right? Because you could actually read through the network almost as fast as you read from disk locally. The other thing is computer got a lot more parallelism, more core, more memories, more disks. And so same thing, right? The ratio of interchange between threads on the same machine versus threads that are on different machine is not the same. So that created a lot of different parameters on how to optimize a query engine. The second thing that happened is the cloud became ubiquitous, right? Like resources are now on demand, right? If you need more resources, you can get them as you need it, and you pay per use, you pay by the minute. You don't deploy a cluster that you'll keep for 5 years and amortized, and then that's what you use, and you better use all of it or it's wasted, and then you cannot get more of it. And the things and cons things, because of the previous slide, is that we had this cloud-based decoupled storage that is fast, cheap, decoupled from compute, and you pay only if you actually access the data, right? So that's also like a big parameter of this. So this led to decoupling storage and compute. And so if you think about, building a cluster before you have storage, compute, and those are tied together, you need to decide how many CPUs, how many disks you put per machine. Now you have storage, which is blob storage, abstracted out. You don't know it's in the cloud. You don't have to worry about it. And then compute is separate, and you can have multiple nodes. They scale independently, and there are a lot of good things that come out of it. So that led to the emergence of the cloud-first data warehouse, right? So I put, initially, so of course, Redshift has evolved a lot since then, but initially there were the two big ones, Snowflake and BigQuery, of taking advantage of this separation of storage and compute. So now you have this much better solution, right? You can store data, you pay-per-use, you grow on demand. If suddenly you have the need this month to do big queries, you can run big queries, you're going to pay for them, and next month you don't have to pay for them anymore. It grows on demand. You don't have the resource contention. If you have the marketing team and the sales team that do queries at the same time, you can give them their own compute allocation, and they're not like competing for the same set of resources, and things are not working. But, we're still creating silos, right? Because you need, even though we decouple storage and compute and it's cloud native and it's in the cloud, you still have to put the data in the warehouse. Even if it's virtualized and there's not an actual cluster, it's in the format of the warehouse for either those two, right? And you can only access it from within. Once you imported the data, you can query, you can create derived data set. The derived data sets are created inside the same warehouse. And then if you want to use other tools, let's say you're doing some machine learning things, or you have other code you want to write on those things, then you need to get the data out. And then if you do some transformation, you get data back in. And so it creates a lot of contention on importing, exporting data. It's hard to keep things in sync. Things can get out of sync. You don't know what's in sync or not. And you're creating new silos, right? So typically what was happening, you had people using SQL in the warehouse, and you have people using other tools, machine learning or other things, building a recommendation engine or something in other tools, maybe Hadoop, maybe Spark. And those were completely siloed, and it was hard to share data. And it's just like what happened because we moved from this data warehouse model, we virtualized it, but it was still its own thing in its own format. So now that we're in this stage, how we look at building a database from those components, leveraging the cloud, right? So we used to do use an existing database, right? So either proprietary, Oracle, DB2, pick your best preference, or open source, or we would build ones from scratch, right? Hive and Presto come to mind as how these things were happening. And building a database from scratch is a lot of work, right? It's an infinite amount of work. It's never finished. And those things took years, and Presto, Trino, I put them in the same bucket. And some of the things you need to think about when building a database from scratch, right, is what are the trade-offs? What are the things, what is the purpose we're building different things, right? Does the data fit on one machine? Does it fit in memory on disk or not? What latency you care about, right? Are we caring about bulk ingestion or being able to query in real time as soon as the data is ingested? You can query it, or you can wait an hour. And is precision important? Can you do sampling? Can you use hyperlog or count sketch as approximate data structures to produce certain things? And that leads to using various components in different ways. So this is my deconstructed database diagram, right? Like if you think of those layers of the database and how you can reuse those components that exist in open source to create a database for your specific needs in that specific use case where you need to optimize performance and latencies and various things, right? So the queries come at the top, so we still have somewhere where you have a query language, whether it's SQL or data frame, you understand, you produce a logical plan, it goes in through an optimizer, you have a physical plan that goes in a query execution, and then you have a storage layer where the execution engine needs to be able to retrieve data efficiently using pushdowns, right? Whether it's filters or projections or sometimes operations as well, and retrieve the data efficiently. And you need metadata from a catalog about the table metadata. And you need to be able to capture lineage, other metadata for compliance, governance reasons. You need to understand how data is being read and produced and lineage between tables. So now I'm going to go a little bit more in those components, those open source projects that enable building something like this. And this applies to a lot of those projects you'll hear about, right? There are a bunch of various open source databases, and a lot of them reuse those same components. So the key components for performance. So I guess one of the more recent project is Substrate. Substrate provides standardized plan, right? So if you have multiple components and you're trying to build this composable data system to make things to work together, and you need to represent operation like filters or projection in a standard way, it's very convenient to be able to use this standard representation and start having a standard way to express expressions, operations, and various operators across project. It's language independent and facilitates push downs. Another, for the optimizer layer, Apache Calcite has become the most used project. There's a couple others, but Calcite is the leading, in my opinion. It's very extensive. It has a lot providing this cost-based optimization experience. It's used in many projects. And it's very extensible. The memory format is Apache Arrow. And there are two benefits to using this. So remember my diagram when I was showing data interchange and want to make that efficient. So one, there's no serialization cost because the in-memory representation is the same as the on-wire representation. So when you copy data, send data from one machine to the other, you just take the buffers, send them to the network, and then when they get from the network to the network input buffer, you can just read it directly from there. There's zero transformation in between. So it makes it really efficient to exchange data between operators, between languages, between machines. And second, it's a columnar format that enables vectorization. So you remember when I talked about the MonadDB X100 use case of needing columnar representation so you can take full advantage of your CPU and speed up the execution. That's the format that enables it. So having a standard representation like this enables reusing those various components. And the last component that I have here is data fusion. So data fusion came out of Arrow as a vectorized execution engine, and it's become really a well-used component that enables you to evaluate those expressions here on top of Arrow representation with a very efficient plan. Right? So instead of building your SQL parser and all the SQL compliant operator from scratch, you just reuse data fusion, and it's going to have all the tricks of vectorization built in, and that's a key component to be able to create those dedicated query engines. And the other thing, just to highlight, we often forget about governance. OpenLineage is my other project. And this is about capturing metadata, where the data is going, where is it coming from, can I guarantee quality, and really tracking how data is transformed and tracking the graph of dependencies between your tables and so on, which is the other important element that enable compliance, governance, and all of those things. So the one component I glossed over in this part, right? This is all about the execution and the top part of my deconstructed database diagram. And the last part, which is really what this conference is about, is the storage layer, right? So if you look at the storage layer in the database, you have a distributed data set with push down, right? So you're able to read the data in parallel from a distributed execution engine, and you want to do this in a way that you don't just scan everything, but you can read only the bytes that you need, right? So you need an efficient format that will enable reading into vectors for the vectorized execution engine. You want to be able to read in multiple streams, and you need to be able to do push downs. Projections is reading only the columns that you need. Filters is avoiding reading segments of the data that are not obviously not part of, not selected by the filters in your query based on statistics. You could do aggregation in the scan itself. If you're aggregating, you don't actually need to read all the rows. You can aggregate in the scan itself and avoid setting them over the network. And things like limits, if you're not reading all the rows, you don't need to read them from disk. So the storage level, in this open source ecosystem, you have two main layers when you can implement this. So one is using Iceberg and Parquet, which is the standard open data lake, right? You store data in your blob storage. It's great for bulk update. It's scalable. It's cheap storage. You don't need to operate any service. The other layer is implementing an Arrow flight layer, which is a way to exchange Arrow format dataset in streaming fashion, in a distributed fashion, right? Streaming distributed datasets. So this gives you more flexibility. It enables finer grain implementation. You can do a lot of tricks. You can do caching. You can do keep track of computation of things. You can make it low latency, transactional, but it's flexible at a cost, right? Because you need to operate a service. So the magic of this layer is the service is your blob storage of choice. There's no service for you to operate. Someone else care about making it reliable and flexible and elastic. Like here, you need to do something. Right, an error flight service, so if we think about this decomposition of compute and storage, you have compute nodes, and then you have storage nodes, and you can use Arrow to exchange data. In the open data lake mode, so using Iceberg and Parquet, the advantage is you have this shared storage, right? You own your data, you have a proper table abstraction, and scalable, cheap, and blob storage, right? So if we, by proper table abstraction, if you think of this immutable data store we're talking about, if you're storing just files in a file system or blob storage, everything gets very immutable, right? You cannot edit a file. If you write things and then someone else is reading them and you have no way of coordinating read and writes and sharing data, then you can not actually change things, because if you change a file, if you append files, you have a lot of inconsistency issue. How do I append a table to a table without coordination and making sure readers are not going to see partial data or inconsistent data? There's no way to do this. So Iceberg provides this proper table abstraction that enables you to do this. So for example, you have snapshot isolation, right? So you can say, I'm writing to a table, but what I'm writing is going to be visible atomically in the future when I say so, when I say I'm done. So there's no phantom read. Whoever starts reading the table while you're writing to it sees the previous snapshots. So things can be consistent. You can also easily implement a rollback because you have a pointer to the previous version. You can easily say, oh, we made a mistake. We go back and restore the previous version of the data, even if I mutated things. So there's this snapshot isolation notion that nobody reads the data until it's been committed. And then a reader that is in process of reading the data, produce something, can always read the next snapshot the next time around. You have a partitioning abstraction, right? So you're not coupled anymore to whatever the partitioning scheme of the writer was. Because of this snapshot isolation, you can have compactors that go and rewrite the partition or change the partition after the fact, and it's decoupled. Like when we shared files in the past, everything had to be coupled from the reader to the writer. All the writers had to understand the partitioning scheme of the reader, of the writer. So this is all decoupled. And it provides efficient pushdowns. So of course, you have statistics in Parquet that let you implement filter pushdown and things like that. And Iceberg takes it to the next level by making this an understanding at the table level and understanding what the table is, and not just a bunch of files and what's a partition and so on. So in this setup, if we go back to this picture of you have an execution engine, right, that can read in parallel, and data is stored in blob storage. So I use this bucket, replaced by S3 or GCS or Azure blob storage or whatever you're using. And all the data-related operations are going to the blob storage service, right? So they scale like the blob storage service, right? There's no other. Of course, you have the Iceberg REST catalog, but the Iceberg REST catalog is just like, oh, tell me where the table is or some metadata about it. But then everything that's read and write intensive going to the data is going to go directly to the blob storage layer, right? And there's very little that goes to the REST catalog itself. And so it's very reliable, or at least it has the same characteristics of reliability as your blob storage. And it has the same characteristics of cost. And so now it's nice. You turn this blob storage into tables. And it's magic. And now you have snapshot isolation. And you have pushdowns. And you can read and write the Iceberg metadata using this service, and read and write Parquet column chunks from your readings very efficiently. And the way we used to store this metadata, we used to, with the Hive metastore at some point became the standard of how you store information over your tables. And it's not because it was great, it's because that's the only thing we had, right? For anybody who operated a Hive metastore as a way to abstract out your files, it's very painful. And now their Iceberg REST API is the thing that saves us all. So I'm also using memes. And so if you think of this open data lake setup, there's a clear separation on what's centralized and what's specialized. So what is centralized is the data. You centralize your data in one place. You centralize in your catalog. And so the governance of knowing who owns what, who has access to what, you can centralize all of this, the collection of lineage, how data is transformed and all of that. So all the usual, warehouse experience of having a centralized data store, and so you get all of this. And now what's specialized, and you can have more than one of, is the compute engine, right? You can have a SQL data warehouse. You can have more than one if you want. You can have use open source query engine. You can use machine learning, AI, training things. You can build recommendation engine that don't use SQL on top of these data. And you can use the next new things that come out, and you own your data, right? It's not like you import it into one tool, and then if someone in your analytics team provides the derived data set in SQL, then you need to export it into something else so you can do your machine learning, and then you output some other data and you need to import it again. You don't have to do any of this anymore, right? Everything is in your open data lake. Is this lakehouse pattern of being able to have your cake and eat it too, right? You don't have to pick and have silos anymore. So there's this nice property, and and so wait, it's all blob storage, right? So always has been, right? Ever since the cloud started to happen and we had like SaaS, cloud data warehouse, all of those things have been in blob storage. And it's all blob storage. So now you may as well use Iceberg and store everything in Iceberg, and you have this shared storage instead of having the data siloed in many different tools, right? So this kind of now it's become obvious that Iceberg has become this standard. And this is the way to store your data and not being tied to one tool. And also it reduces enormously the ability to try new things and try the new tools, right? Your data is not locked in one solutions anymore, and you can try a lot of new things. So on that, I realized I spoke a little fast, so I went through this. So we have time for questions. That is a good thing. I also, after the break, if you want to hear more about how Datadog uses Iceberg, you can go see Mark's presentation in this same room. And on that, I'll be happy to take questions.
So yeah, you just touched based on the lineage, right? So in open lineage, using open lineage today, like any like commercial version of using open lineage today available for usage. I know. So I'm from Boku. Like we use a data hub, but not very happy with it. But yeah, just looking at any other solutions.
Okay, so OpenLineage, you can see it as open telemetry for data, right? So for example, I think DataHub can ingest OpenLineage, and there are integration. So there are several commercial offering that ingest OpenLineage, and actually it's been adopted by the major cloud providers. For example, if I take GCP as an example, when you use GCP as a metadata governance offering called a Dataplex, and when you collect lineage from the Dataproc Spark job into Dataplex, you use OpenLineage. So Dataplex accepts OpenLineage. So I don't know if you use Google Cloud. If you use Google Cloud, you can use Dataplex. If you use AWS, they have a product called Data Zone. And similarly, when you get lineage from your jobs, you can get them in Data Zone. There was a presentation at the last AWS conference. And if you use Azure, their governance product called, I'm blanking out, sorry about that. Anyway, they support also OpenLineage, right? So it's been adopted by the main cloud providers. There's a bunch of other companies that supports it, like Astronomer, former employer, accept OpenLineage to do monitoring of your Airflow jobs. Some of the most popular OpenLineage integration, there's a Airflow integration, which is built in Airflow, so you get lineage out of your Airflow jobs. There's a Spark integration that uses the Spark query listener. You can get your lineage from Spark. There's a Flink integration. So there's a very good ecosystem now, and I'm mentioning the cloud providers because they're the biggest ones. Obviously, usually people use them, but there's also a bunch of startups or different tools that are leveraging OpenLineage, either for compliance, like if you have GDPR or things like that requirement, or BCBS 239s for banks, or for data reliability, data quality, connecting the dots, right? Usually when you have data quality problems, the problem is upstream. Someone has messed up with one data set, so you need to follow lineage to figure out where it's coming from. Yeah, OpenLineage has been working very well. It's growing well. There's good community. Yes. Oh, yeah. Yeah.
Is that
No, but it's recorded. That way they can hear your question.
Okay, sorry. Yeah. Is that data lineage tool for Trino? Yeah.
Yes, there's a Trino integration. I'm not super familiar with it. I think that came from the community. Yes, there's a Trino integration for OpenLineage as well.
Okay.
Yeah. Should have made an OpenLineage talk. Lots of questions. Go ahead.
Hey, Julien. So in Iceberg, you mentioned that writer and reader partitions can be different, right? Like it can be repartitioned. So is there an assumption that once a partition is written, like it will never get any more files? Like what happens if the writer writes to the same partition again? Like
so
the reader has already
what I meant it's decoupled, right? Like because it used to, when we used to do folders based, and you would have a folder for the table, and then you have a folder per partition, maybe per month or per day or something, right?
Right.
And then you have files. We were tying together readers and writers, right?
Okay.
And like the reader had to understand the partitioning, and you cannot change it after the fact. In Iceberg, it's abstracted out.
Okay.
So it's decoupled, right? Like the reader doesn't have to know anything. Maybe the data is not partitioned. Maybe you change the partition after the fact. Because of the snapshot isolation, ability of Iceberg, you can actually change the partitions after the fact, right? The writer maybe writes, and actually people do that sometimes, right? If you ingest from streaming, maybe you rewrite files every minute or every 5 minutes, right?
Yeah.
But then you end up having too many small files, which impacts reading performance. So you will have something else. You will have a compaction job that will go there and rewrite those partitions and partition it by day or by months, or I don't know, like per hour. It depends. Right. And then the reader doesn't even need to know about it. And you can even change your mind later and say, like, you know what, now we are going to partition it differently, or we are going to sort the data. And you can do this atomically without breaking any readers, right? We created this synchronization mechanism that makes sure the readers are not going to read partial data that you're modifying.
Right. Yeah, that's true. So when you're repartitioned by day, let's say like for that day, like you got some new writes, like 7 days down the line, right? Like, so would anything like again go and repartition it? Or like, is that like part of a regularly scheduled like compaction job, like typically?
Yes, it's up to you, right?
Okay.
So now you can have concurrent writers to the same data, right? You can have the job that happens new data to the table, and concurrently you can have a compactor that does some maintenance and rewrites those partitions, right. Or maybe it splits it in smaller partitions, or it compacts in fewer partitions. Or if you have something that went and deleted for GDPR, you had a job that said, hey, I'm going to delete all of those things.
Okay.
And you created a deletion vector. You can have a compactor that comes later and actually remove this data. And it can all happen concurrently, right? You can change the partitioning, you can modify concurrently the data without creating inconsistencies, right? You have this nice... Am I answering your question?
Yeah. I got that. Yep. Thank you. And the second question I had is regarding the Arrow flight service.
Yeah.
So when would you run that, like as opposed to just reading like from Iceberg?
Also, one example: if you're a company that stores a lot of time series, let's say you collect metrics, right? Okay. And metrics are like partial aggregation, right? You're collecting, you're seeing events, you're counting them, or you're collecting a gauge, and you're doing partial aggregation, and it goes in your store. And you're very interested in a low latency ingestion. You could implement an Arrow flight service that ingests the data, and once you make sure it becomes available to the query engine as fast as possible from ingestion, right? You have a time, because let's say you have monitors that are going to run query on it to evaluate whether an alert should go off or something. So that would be one example, right, of querying data. Also, S3 adds latency. When you query directly from S3, you add latency. Right, S3 is higher latency than a regular, if you store in SSDs locally on the machine.
Right.
So you might want to have like cache layers, right, that keep some of the data most queried in memory or things like that, right? So that's kind of some of the examples of things you could do.
Okay, thank you. Yeah.
Hi.
Hi.
When you were talking about like creating the daily tables from the hourly tables thing,
yeah.
How is it different from, for example, creating different tables, like aggregated tables from the hourly table?
But you don't have to duplicate the storage, right? In that one. So in one case, if you have two tables, right? Let's say you're collecting the data every 5 minutes, and then you compact it to another table every hour. Right, so now you're storing the data twice, right?
Right.
And you need to have the foresight of creating two tables up front, right? And if you do it systematically, it can be expensive, right? So with Iceberg, you don't need to think about that, right? Because you have a table, maybe you're adding data every 5 minutes. And the reader doesn't need to know about partitioning. It's like in a regular database. Partitioning is abstracted. You're just saying, I want data from this time to that time. And Iceberg will figure out which partition you need to read, right?
So the daily partition is actually accessing the same hourly or lower granularity files, right?
No,
you're not actually duplicating the data here.
You rewrite the data, right? So in Iceberg, you can, so what you're going to do, you have all the files of your data. Someone adds every 5 minutes. On one end, the writer writes every 5 minutes. On the other end, you have a compactor that every hour is going to look at, give me all the smaller partition for this hour. I'm going to read them, create a new partition for the hour, rewritten with bigger files, so they're going to be more efficiently accessed for read. And now in the metadata, I'm going to have a pointer with the previous version, which is what's called a snapshot in Iceberg, right? That says this is a table V0, and this is a new table V1. It contains the same data, but I rewrote it. And then you keep both for a little bit of time. So there's some duplication, right? This partition has been rewritten. There's some duplication. And then the readers will read the new version, right? And then over time, you can say, well, we are going to delete these older versions over time, right? So you can rewrite the data atomically, right? Because in the metadata, you said there's a previous version and there's a new version of the table. And this mechanism can be used for deleting data, mutating data in an atomic way. And you can have someone reading the old version, and it's not going to be impacted because the old version doesn't change while the new version is being created. The next reader will read the new version. And then after some time, you can delete the old versions, right? That's kind of part of a maintenance job, right? So the main thing is this enables concurrent writing to the table without creating inconsistencies, right? You can rewrite partition, you can go to 5 minutes partition to 1 hour partition. You can change your mind later and say that, you know what, we're going to make daily partitions actually. Or, and everything will keep working. You don't have to create an additional synchronization of all the other reader jobs while you're mutating your table.
Great, thank you. So the choice is with me basically whether I want to keep the old lower granularity data or I can delete it, right? If my application needs hourly data, I can still keep it as an older version in the snapshot basically.
Yeah,
right?
So basically when you have your maintenance job, you create your own policies of how long you keep the data. Like for example, if you have GDPR requirements and you say, you know what, we need to delete all references to this user, you have a job that does a delete. So you're going to have the new version where the data has been deleted. And the old version is still there for a while because of this. You want to not break what's reading while you're doing this. And after a certain amount of time, you're going to have a maintenance job that actually deletes the old versions, right? And let's say you have 30 days, I think, for GDPR to do so. So you will have a policy when you say, I want to compact everything, like remove old versions after 30 days.
Got it. Thank you.
Yeah. So if you delete something you didn't want to delete, you can go back to the previous version for some time. And I think we're at time. I've been told they forcefully expel you from the room if you go over. You're doing that? No. Thank you.